Thank you. I've been working for S&C Electric and its predecessors for close to 40 years. And we've been doing grid forming inverters for our UPS systems for 20 years. So just a quick timeline. In '97, we started working on our first grid forming systems for a 2 megawatt UPS system. In 2006, we started working on a distributed energy storage system with AEP that we eventually renamed a storage management system. 2008, we modified the grid following to be a grid forming inverter. In 2010, we started working with the CERTS algorithm for the Santa Rita Jail project. In 2012, we're working with a UPS where we started using frequency and voltage droop. In 2014, we went to full-time operation as a grid forming inverter in that UPS. I've got a little bit of a talk on one of our 250 kilowatt systems, and then some of our end developments. So, our first UPS started with 8 250 kilowatt battery modules. And so this was an offline UPS. We used a thyristor-based power electronic switch. When we saw a problem with the utility, we would open the switch and run the inverter to cover the load. It used an analog voltage regulator, and in order to control the 8 inverters, we sent the same switching signals to all 8 inverters. So each one was getting those through fiber optics, and we got sharing between the various inverters using output inductors. Here's a picture of a 4 megawatt, 5 MVA system at a NASA Deep Communication Space System. Each of the little RV air conditioners is one inverter battery set. Those are used to keep the batteries at the right temperature so that we can warrant that system. Whenever we went into the UPS mode, we just run at a constant frequency. And we do that for a while. All of these systems had generators because we had a very limited runtime. And so when a generator would start, or if the utility would come back, we would synchronize to it because we had voltage measurements on both sides of our power electronic switch. So we could resynchronize and transfer back. One of our concerns was when we transfer back to the utility or to a generator, how do we keep control of power? And so what we did was when we transferred back, we go to a grid following mode so that if our angle was a little bit off, we still had control of power. And so that UPS had initially a 10-second runtime, then a 30, and eventually a 60-second runtime. The 60 seconds is limited by the batteries we're using. They were lead acid batteries. So what are some of the problems that that system had? First of all, because we had in our lead container, we had our regulator board. If we tried to run too many modules where we weren't measuring the currents, we lost stability. And we found that somewhere around 5 inverters was necessary in a multi-container system to maintain the stability. We also had to do derating because the power sharing wasn't that good. So as we went from a single container to multiple containers, we were sharing through both the output inductance and the inductance of the output transformers. And these are all applied at medium voltage. And so we wanted a system that would let us take any container or inverter offline and have a minimal derating in power and allow us to better control VARs. So as time progressed, we started our next inverter development, which was a system that worked with a fairly large battery. I've got a picture of one of our early systems that was using grid forming. You can see 2 transformers are the green boxes. Those are 1.5 MVA transformers, 2 inverters between the green boxes and off to the edge of the picture. And then behind those was the battery. This is a sodium sulfur battery. Each box was 1 megawatt, 6 megawatt hours. So this is a 12 megawatt hour system. So in this case, the master control would send an angle and a voltage for the various inverters to run at. And to get sharing, what we did was we would measure at each inverter the power and the VARs, sum them up, send the average back, and then for sharing power, we change the phase angle to get the power to be the average power, and to share VARs, we change the voltage in order to get the voltage sharing. That was done with data that was running at about 5 kilohertz out to our master control and back. So still highly communication need system. So in order to see how well that worked, one of the things we did was we put a 480 volt load bank at the output of one of the 2 inverters. And so one inverter was feeding that load bank directly, and the other inverter fed through a transformer to the medium voltage system, back down through a transformer, and to that same load bank. And so with this system where we would send the average power in VARs, we were able to balance up that power in about 2 seconds. So that gave us nice information, but we needed to have good power and VAR and high-speed communication. So the next system that I wanted to talk about was the Santa Rita jail microgrid system. So this is a system using CERTs that had a 2 megawatt lithium-ion battery from BYD, a Chinese company, 2 750 kVA diesel generators, a 1 megawatt fuel cell running in the grid following mode, and 600 kilowatts of PV also running in grid following mode. The diesel generators were normally not on, and then what S&C provided was the battery inverter. So in this case, we started running in parallel with the utility in the grid forming mode. And my concern was, okay, as soon as we do that, we've got the fault current of the utility that, as an example, in our shop was on the order of 40,000 amps and could do some nasty things if you got the angles wrong. And so we've been concerned about that all along. So when we started running this system, we synchronized up, turned it on, and it was really boring, which was great. It just worked. And it stayed at the power level that we had commanded. When we commanded a new power, we go to that new power. It worked the first time right away. One of the concerns we had was, okay, if we're a voltage source and we're running in parallel with the utility, what do the current harmonics do? So at our shop, we measured what the current harmonics were. They were actually within limits, but the sort of the unfair thing is our utility voltage harmonics are on the order of 1%. So it was a pretty clean utility, clean inverter, so we didn't really have any current harmonics. So in addition to running just sort of with utility, we wanted to see how we shared with a diesel generator. So in our shop, we did some testing with a diesel generator. The top curve is our A-phase voltage. This is a 3-phase system. We have all 3 voltages, but they all look the same, so I just have the A-phase. Down below, we have the current out of the inverter, and that's in red. In pink, there's the power coming out of the inverter, and that's been offset so that you can see it. And then down in black at the bottom is the frequency of the inverter, and that's also been offset. So here we had about a 500 kVA generator, so we would add 300 kilowatts of load, and then later we subtracted it. The timeline here is about 35 seconds. The small divisions are half a second, and the bolder divisions are 2.5 seconds. So you can see that as we added load, the inverter was able to grab the load that was necessary. You can see the voltage up above. You don't see a problem. There may have been a little dip there that's been run over. But then as we drop the load, you can see just the tiniest little disturbance up above and below where we have a little bit of an overvoltage, but as you can see, that's a pretty minor overvoltage and very short. This is what that system looked like. We had 2 inverters inside an ISO container, and then back behind it, the ISO container with a little bit of blue on the top of it is the BYD battery. So after doing that project, we started working on a new UPS system. So we called it a UPS XT because we were extending the time from what we had gotten up to, which was a minute. And then we had time that was really set by batteries. We do most of that with a 5-minute battery, but we also had a half-hour battery at one of our early sites. So it's not limited by time any longer. We have multiple 2-megawatt blocks. We can containerize the 2-megawatt block with 5 minutes of battery and a 40-foot ISO container. And so I'll go outside with that. Still an offline UPS. Now we have a remote master control, so we don't care what inverters are online or offline. And we have grid forming inverters that are running both voltage and frequency droop, where the need for communication is really a slow need rather than a fast need. So they just adjust to the new voltage and VARs very quickly. Our first system used 8 inverters with 6 2.5 MVA, 1 megawatt, 1.25 MVA inverters with 6 2.5 MVA generators. And then we were able to reconnect because we ran at a different frequency. We would reconnect by looking at the voltage and phase angle across the interface, send new power or send new frequency and voltage commands to line up with the frequency and then transfer back power. So usually we knew whether we were transferring to a diesel generator or to a utility, but then we got to a site where it was so redundant that they could put the diesel generator either on our input or our output and didn't really have a way to tell us if we were connecting back to the utility or to a diesel generator. So what we found was when we transferred back to the utility as a grid following inverter, when we were lightly loaded, we had a small signal instability. So we changed that to use grid forming, got rid of that problem, and that's how we left the system. So we've got continuous operation and grid forming mode now with those fairly large systems. We had another site where we had a small 250 kilowatt inverter where it was coupled with a couple small generators, sort of an island system. The inverter was there to help support the generators, but it was running in a grid following mode. And what we found was in that mode, while everything was stable, the generators couldn't keep up with the changes in load. And And so we'd see frequency and voltage variations that were beyond what they wanted with the steps that they were putting on it. So we switched over to a grid forming mode and everything stabilized out. Our last development was an SMS liquid cooled inverter. One of the things we liked about the liquid cooling was we could optimize it for power without overload, which was what we were doing initially, but we could also reduce the cooling system and have a lot more overload if we wanted to handle systems that needed more overload. And we're looking at, can we run in the grid forming mode all the time and still meet the existing standards? So that's what we're pushing toward. But unfortunately, our company made the decision to let us get out of the inverter business. So we stopped working on that. We also have a studies group within S&C. That studies group does modeling of the utility system, and they help us to apply our inverters with other people's inverters. And so the person, Steve Williams, who headed that up, and I worked together quite a bit. And he was seeing that if we were running in a grid forming mode, we were much more stable than if we ran in a grid following mode, in particular in weak systems. So that showed that we should really be looking at more grid forming inverters on the system. And in one case, we had a lot of existing grid following inverters, and we looked at adding grid forming inverters to see, you know, for a pure inverter mix, where would how many grid forming inverters would we need to stabilize it? And we ended up with about 1 per unit of grid forming inverter would handle 2 per unit of grid following inverters. So, in conclusion, we've been using this for a long time. We've tried a lot of different ways of doing grid forming. But once we started using frequency and voltage group, it became clear that that was a system that met Scott's keep it simple, very easy to understand. And so that's what we've been doing since that time. The nice thing about using that type of system is the communication can be very slow. So as we all know, communication can be problematic. We were pretty lucky because our systems were very tightly coupled. And so we use Ethernet communication, 100 megabit per second to communicate between inverters. That all works really well, but that doesn't work so well as things get spread out on the system. We also make radio systems, and that's a major problem for our customers when the radios go down or are intermittent. So we really wanted a system that was insensitive to that communication speed. So overall, we think that using more grid forming inverters is the way to go, and we are firm believers in frequency and voltage group. So, thank you.
Great. I guess we have time for a couple of questions.
Can you give me a feel for the costs for a grid forming inverter versus a grid following inverter?
Sure. In our systems, we put the controls in to do grid forming or grid following. The controls are actually a little simpler for the grid forming inverter than they are for the grid following inverter, because what we do is we measure power in VARs. We change our frequency based on power. It's a very straightforward system. What it really comes down to is most grid forming inverters need to have some overload, where the grid following don't necessarily have to have the overload. But if you look at the same capability, in the steady state, they're basically the same cost as what we found. Now, if you need overload, you can get overload that isn't steady state at a lower cost than steady state overload. So it sort of depends on how much overload you need. And with our early inverters, we were able to overload to about 2 per unit for a short period of time because we had headroom there. But in our latest inverter, we were trying to optimize for lowest cost per watt. So if we have no overload, that maximizes that. But then to get the overload, we would just back off on the steady state rating, back off on the cooling, steady state cooling, and come up with a little lower cost.
I guess we'll take one more question if there's any, while I also request the next speaker to come up and set up.
Thank you for your presentation. I know you delivered many different inverters, but you said you use a group control. I see you use some surge group and some other voltage and frequency, but they're the same. All the same group control out there, any slightly different in the surge group.
Right. So the difference is how we're commanding the droop. So in surge, we're commanding power, and the other way to do that is just to command frequency.
I guess there was one more question. This one.
Thank you for the presentation. So I did notice that towards the very end you were looking at liquid. But do you have any thoughts on how cooling the cooling might? So why do you use by the provide those short bursts of overloaded capacity while ensuring that there's sufficient protection as well for the inverters to stay? Thermally is one of the important constraints of the grid.
Right. So you can certainly go a little bit higher in capacity if you have put that headroom in. We're using a smart IGBT, and so it was limiting the amount of power that we could take sort of instantaneously, and we were pushing up against those limits. So we didn't have the same capability to do overload that we would have had if we hadn't had that constraint from the IGBT. But that only got us a little bit of the way in any event. To get to good overload, we really needed to get that water system down in temperature so we could really make use of the extra delta T.
All right, let's thank Dave again.